Good evening, everybody. I'm very glad to open the second part of the workshop. We're going to have two talks and then a lot of time for discussion. So I think that we saw that there is a lot to discuss. So we'll have time for that. So please write down your questions. We'll have time for them. So the first talk is by Amichai Gal. Amichai is a retired senior intelligence officer currently, an MA student here at the Cohn Institute of History and Philosophy of Science and Ideas, and is interested mainly in history and philosophy of physics. He will tell us now on the multiple invention of thermo-nuclear weapons.
So here you can see the American H-bomb and the Russian H-bomb, the first one. As you can see, they're very similar, and we're pretty much finished with this. But we're going to go a little bit back and forth. So a multiple invention begins to be epistemologically interesting only if you can show that it's actually a case of multiple inventions. For that, I think we need to show three things mainly. One is that we're talking about an invention who's actually not an incremental change of other inventions. It's something innovative. Obviously, it's not a very definite thing to say about an invention, but in this case, I'm not going to stop at this point because in this case, it's pretty obvious. The humanity did not have H-bombs before this, and they do after that. It's a very big change in what people can do in the warfare. Stupid change, but that's a political thing. And we're not going to focus on that. We are going to focus on the other 2 points, which is we need to show that the two inventions are similar enough. Obviously, it's difficult to say what similar enough it actually is, because no two inventions are never the same thing. But we need to see that at least they are similar enough that we can relate to them as one and the same invention. And we need to show that they are independent and not one person or one group following up on another group's work. So for that, we're going to follow this by following the timer. And we'll see the similarity and the independence of the two inventions through this. So, 1941, the very idea of a thermonuclear weapon of an H-bomb is born in the mind of Enrico Fermi in New York. War is already started, not for the US, but for the others. All the physicists, the nuclear physicists, are well acquainted by this time with the fusion, the split of the atom that was discovered in the early 1939. Still, when the world was not at war and the paper was circulating, and everybody learned about it in the US and the USSR and Germany, and Germany was discovered in Germany, and Britain, Japan, and everywhere. And many people thought, as the war started, that this new idea, this new discovery, the fusion of the atom can be turned into a weapon, which we all know actually happened a few years after that. And these thoughts they were contemplating in Germany, they were contemplating in Britain, later on in the States, also in the USSR at the beginning of the war. Everybody was thinking that we can take this split of the atom thing, the fusion, and make it into a bomb. By 1941, already the Brits have already started the nuclear project, later to be merged with the American one. The Russians were thinking about it just before the Germans attacked them in the summer of 41, etc. But what is different here that this scientist, Enrico Fermi, he meets Edward Teller in New York, and he says to him that he has a new idea. Why don't we take the atom bomb, the fission bomb, that we don't have yet, but we're thinking about it, we're going to do it. Why don't we use the tremendous heat that it generates to produce a fusion bomb? That's the basic idea. The fission bomb, the atom bomb, is supposed to, because we don't know it yet, they have calculated it, but they haven't done it yet. They're thinking it will reach at its core hundreds of millions of degrees Celsius. which is way more than the minimum needed to make two light atoms fuse. So that's the very basic idea. Teller tells him it doesn't look very good. He does some calculations and tell Fermi it will never work, and they both forget about it. But Teller is interested, he thinks about it for weeks, and he gradually becomes convinced that it is possible, and this becomes his life quest, maybe his obsession. The Russians at the same time were attacked. This was in September of 41. The Russians were attacked in the summer. They are in the middle of the war. They were thinking about nuclear stuff, but the nuclear center in Kiev is occupied, and the nuclear center in Leningrad is under siege, and the nuclear center in Moscow was transferred east because nobody knew where the Germans stopped, and so forth. So this only happens in the States at this time. Project Manhattan Project is launched 1942. They are aiming at the atom bomb, obviously, as we all know. But Teller is already obsessed, and he succeeds to get a budget and some small team of theoretical physicists, and they start working on this idea. I would say low-intensity research because most of the money and most of the people are going to the main project, which is obviously Russians are still in the same thing. A few years go by, the war is ended, the atom bomb is also is achieved and dropped on the Japanese. And the Americans in August and September 45, they Fermi gives a few lectures in Los Alamos in the laboratory, trying to summarize the research they did in the last 3.5 years, and it's more or less at the same time. The idea is born once again in Russia. At this stage, September of 1945, they don't know yet. The Russians don't yet know what the Americans are doing in this field. They obviously do know that the Americans have bombed Japan. Everybody knows that, and they start their atom bomb, the fusion project, following the success of the Americans. But they also one of them, Yaakov Frankel, a physicist, he writes a memo to Kurchatov, which is the head of the program, and he suggests the exact same thing. He says, why don't we use some hydrogen to enhance the energy output of the bomb we are thinking about, which he describes it in a very similar way of Fermi. But none of this is not an invention, it's just a basic idea. An invention, it's hard to decide exactly what it is, but it's definitely not the basic idea of it. It's much more than that. So two more things happen in this fall. One is the independence. We're talking about similarity and independence. Now let's go to the independence. All the blue arrays are independence stuff. So one of the attendants of these lectures in the fall of 45 is Fuchs. Mr. Fuchs is a physicist. He used to be German, now he's American and British a little bit. Klaus Fuchs. He's also working for the Soviets. He listens to them, and he brings to the Soviets this knowledge, the knowledge that the Americans have in September 45. So I would say that he makes the Soviets equalize their knowledge with the Americans, just by the starting point of their thermo-nuclear program in October of 1945. And they also start, just after that, a few weeks after that, what I would describe like a low-intensity research program. Again, because this is 1945, they're working on their atom bomb. They will conclude this work 4 years from now, in 1949. So for them, the thermonuclear thoughts is something for the later future, and that's why it is a very low intensity at this stage. Let's go forward a little bit. What is the idea everybody is working? When I say low intensity here and low intensity there, what actually is the idea they're working on? This is a sketch that this Klaus Fuchs person, this is the sketch he gave to the Russians in 1945, but it serves as the general demonstration of the general idea. The idea is very simple. This is an atom bomb, and just next to it, there is a container with hydrogen, in this case, deuterium and tritium, the higher isotopes of hydrogen. Simply because hydrogen, we need a few hundred million degrees, which is more difficult to achieve. But with deuterium and tritium, we need just 100 or 50 million, which is a little bit better and more in line with the energy that the fusion actually yields. So the idea is we produce a tremendous amount of heat here. Here is a container with deuterium and tritium. It will ignite in the sense of the fusion. It will, the energy will be high enough, temperature will be high enough for the fusion to occur. And after that, it will propagate in this container. And it was left open on this side for a reason, because it's supposed to show that we can do it as big as we want. We can do the if the actual fusion propagates, then it can be as big as we want, and the energy output would be way bigger than the atom bomb, maybe 1,000 times bigger. It depends on who you ask on this stage. For this to happen, we need to show, they needed to show two things. One, that it ignites, and two, that if it ignites, it actually will be propelled, will propagate through this tube. And that turned out to be very, very difficult to do. They couldn't do it. They were working we're now in 1946 for 4 years in the States and a year in the Soviet Union, and they couldn't show it. Now, tests were out of the question at this stage for many reasons. They needed to show it in theory, and they couldn't do it. And they tried different configurations, and they couldn't do it. By the way, it's very difficult. Also, they don't have computers yet. We're talking 1942, 1946. They don't have yet computers available to them. So we're going a little bit further down the line. We're now in the spring of 46. In the States, this time in 46, 47, 48, 49, there's a really, really low intensity research. Nobody cares about it. The army doesn't want this. The army wants the atom bomb deployed in a better way, not like in 1945 it was just the beginning. Now they wanted to build an arsenal. The politicians are not applying pressure on this project at this stage, and there's a very small scale research going on. Of course, Taylor leads it. By 1945, most of the scientists left Los Alamos and went back to their civilian jobs. So did Taylor, but he comes back every holiday he can to Los Alamos and tries. And then Soviets at this time are still with the same thing. So he comes with an idea. Because they cannot calculate what I said before that they needed to, he comes with this idea. He calls it the alarm clock idea. So what is it? He says something like this. Instead of having an atom bomb here and a container of hydrogen, why don't we put the hydrogen around the main bomb? What do we get from that? If the temperature is high enough to ignite it, then we don't need, it doesn't have to propagate, because all around this sphere will ignite at the same time. So we have a large mass of hydrogen all ignited at the same time, and we can solve the problem of propagation, which was a very difficult problem to solve, at least in calculations. That's his idea. And he says, more than that, we can do that more than once. We can put an atom bomb here, and then here is deuterium, which is the hydrogen, and then here's another uranium layer, which will, because this, if it does ignite, it produces very fast neutrons, so it can produce another fission, another atom bomb of this, and then goes again second time. So that's the basic idea. It is brilliant, it is different, but they decide not to go for it. And they very recently never heard about it again in the States. And the reason is not very easy to understand why. Well, I read many reasons. For instance, as a practical thing, they thought this would be very big physically. The diameter should be at least 150 centimeters, maybe 2 meters, which was bigger than the missiles they have. They were afraid that they go for it and they can deliver it in a missile. And in the 50s, they were thinking about missiles at this time. They didn't have it yet, but they were already thinking about 3, 4, 5 years from now. But I think the most important reason is not that. The most important reason is that this is a project of Elor Teller. He does whatever he wants with it. There is no political pressure on him or anywhere else in the project, and he doesn't want it. He doesn't want it because this cannot go far enough. This is you cannot, for reasons I'm not gonna. No? Okay. So he decides not to go for it because he wants to go in the megaton area energy and not a few hundred kilotons. So they left this. We go 2 years later, and we have the second and last equalization, intelligence equalization. Fuchs brings the Soviets in 1948 to the same place where the Americans were before this invention or this idea. Why 2 years? The Soviets had problems contacting with him, and they lost contact with him for a couple of years, and then they re-established contact, and he told them where the Americans were here. But he didn't know about that because he has left in the spring of 46. He left the project and never went back. So there is no evidence after this that any intelligence is flowing either way. So after 1948, it's pretty clear from available information that these two projects are independent. Second thing that happened in 48, a few months after that, in September, Andrei Sakharov, 27 years old, brilliant young physicist just out of PhD, joins the project. He hasn't been there for the last 2 years. He's the fresh person, and he comes with the exact same idea. He calls it the sloika, which is the layer cake in Russia, and it is the exact same idea. You can see the paper he writes, it is the same idea. Why don't we put hydrogen around the atom bomb? Both are okay. Last 2 years after that, the Americans go public. Truman announces that the project will occur. Now, the low intensity becomes in the States big intensity, very big intensity. It's a big project. Now they need the atom bomb. It's after the Russians have the atom bomb. They think they need the H bomb, and they go for it with all the power. The Russians are working on the Sloika. They are making it work, and they're working for like the next 3 or 4 years into making it happen. But just when the Americans go public, they find a problem. Stanislav Ulam, a mathematician, finds out that this super bomb, the one I showed you before, the one that has to propagate, can never work. It will not work. He shows it mathematically, and he does these calculations. Very interesting, but they're pretty sure, while the Soviets continue working on the Sloika. Few months after that, he comes also the same Stanislav Ulam comes with a solution. He has a brilliant idea. He says, why don't we take this huge energy that can destroy a city, as we've seen in Japan, and put all this energy into the compression of the container of the hydrogen. He thinks that the compression can be done with the shockwave. When he showed that a couple of weeks later to Teller has a very big breakthrough. He said, we can do this, but we can do this with radiation implosion. What happens is that 80% of the energy of the atom bomb is at the first stage radiation. This radiation reaches the hydrogen in few nanoseconds. The shock wave is slower, way slower than that. It goes like 1,000 kilometers per second. So it will reach in the microseconds area. It's a long time after that in the relevant time frame. So his idea is this one actually. I don't have much time. So the basic idea is to use this energy to create an equilibrium between the energy and matter temperature, which will, well, since I don't have enough time to go into the technical details, so I'll leave it like this. What happens then? They are very happy with it, the Americans, and they start to work on this idea. That's the big idea. That's the parallel idea, the one that we, in a few seconds, I'll show you happens also in the USSR. They go for this for a test in November 52. A year and a half after that, they test it and it works. The Russians are working on the Sloika, the same one, and by the summer of 53, they test it and it works also. But then they already know that the Americans have a way bigger weapon. And in the Cold War, which already is evolving, by this time it's a very bad idea for the Soviets. So they need to find a way how to get their bomb way higher in energy yield. And the Sloika cannot be enlarged too much for technical reasons, criticality to be exact. And then Sakharov and Zeldovich come up with the same idea, the exact same idea. Like the first Ulam's idea. They say in the paper, this is the drawing. Why don't we take an atom bomb, a diaphragm, which I omit because I don't have time to explain, and the Sloika, which is not the exact same idea, not exactly the same thing. We take the Sloika, and then it already have some elements but I didn't have enough time to explain. And this is the very idea, but they're very specifically said, we are going to use the shockwave, the physical, mechanical shockwave to compress the Sloika. And then both of them.
Can you conclude?
Yeah, I'm in a minute. Both of them are the leaders of two departments, different theoretical departments. They go to work, and within 3 months, gradually within the department emerges the second idea of Tether. They understand that the idea is great, but the shockwave is not good enough, and they come up with the same radiation implosion of the idea. They don't call it this way. In Russia, it's called, until today, it's called in a different name. It's not very important, but it's a very same idea. Technologically similar, not the exact same. And a year later, they also take a year and a half to make a deliverable weapon. The Americans, around the same time, finish making the H-bomb the deliverable weapon, and they all test it, and the pictures I started with. That is it. Now, last remark is, what do we learn from this in a more broader sense of the multiple inventions? I think that the most important thing that I understand from this is that there's a difference between, there's a very strict difference between scientific discovery and technological invention, in the sense that these people have a very concrete and specific target. They need to reach a fusion weapon, and that is, I think, in my mind, is highly heightens the probability that they will solve their problems in similar ways, considering that they have they are sharing the same theoretical data, which is nuclear physics. That's it.
Thank you very much, Amichai. It's really interesting. There are many questions, but we'll keep them. We first have Shaul's talk, and then we'll have the broad discussion. So it's a pleasure to introduce, without further ado, Professor Shaul Katzir, an historian of modern physics and related technologies here at the Department and Institute, in Cohn Institute for the History and Philosophy of Science and Ideas. And among other projects, is currently studying the phenomenon of multiple invention in technology.
Thank you very much. I don't have a presentation. So, I start to be brief for time. So my project on multiple inventions in technology examines particular cases of contriving a similar device or method independently by separate individuals and this phenomena in general. The project aims at better understanding of the appearing of such duplications and through them of inventions in general. Traditionally, multiple discovery has received more scholarly attention, but despite important differences between the two and between science and technology, we can learn from inventions on discoveries and vice versa. Here, I will concentrate on the process of innovation, that is on the invention and its lessons to discoveries, and less on the causes leading to inventions and their multiplications, which occupies much of my study. Practically, I look on our requirement from a deed to be regarded as an invention or a discovery. To save replication, I will refer mostly to inventions, but mean also discoveries. My reflections are based on a list of 150 probable multiple inventions, a few dozen of which were examined in varying details by my collaborators and myself. We'll see if I will have time for a further non-multiple example on, we'll see if it does. Okay. It is virtually impossible that two inventions would be identical. Yet, my analysis of multiple inventions showed that a precise definition of the invention that identifies its essential properties can allow one to determine whether two devices or methods were similar enough to be regarded as multiple, or basically equivalent. Such a definition should be based on a concrete function and its specific materialization in the device. Unlike the thermo-nuclear weapon that has a very clear function, if you like it or not, and also has clear, the Aharonov-Bohm effect had no function. Instead, in that cases, we should look on the concrete claims made and their meaning, and empirical consequences of the discovered propositions, as understood by the protagonists. The counterpart for materialization in discovery is probably empirical verification. Is it necessary for turning a prediction? Is that necessary for turning a prediction into a discovery? Actually, we already touched this question at the end of the last session. So I'll leave it for discussion. The invention process should include the inventor's recognition of its function. Inventions are not accidental, but have intended purposes, even if they may originate in serendipity. Finding a new use to an earlier device is a new invention. So, if you think of the invention of the triode, the free electrode valve by Lee DeForest in 1907, is probably a very important invention, but it's not the invention of the regeneration tube circuit the one that allows us to have amplification, because this was based on the triad, but Lee de Forest did not know how to do it, at least not in 1907. There is a question whether he managed himself to do it 4 or 5 years later. Others, that's for sure, managed to do it, but this is a different invention. Likewise, the process of discovery includes recognition of the claim and its basic significance, even if not all its consequences, which of course should not ask for that. Observing an outcome without recognition that it is due to a previously unknown effect or phenomenon is not a discovery. Apparently, this was the case with some of the early observations that we can interpret it as cosmic microwave backward radiation, Natasha showed before. In my work, I've encountered a few cases like of this kind of earlier observations, which are not discovery, of much less famous effects, such as ferroelectricity. Still, there is, look on the Web of Science, you see there are quite a few thousand papers on that every year, which we can see in some reports from American military in the 1918, that there are some observations that are connected to what was later understood and researched as ferroelectricity. And also I could see it also in the work more in the laboratory notes of one of the same scientists who had observation and only a few months later returned to it to make a discovery out of an observation. A case in which the original discoverer's interpretations of her finding disaccords with the current view is, I maintain, a discovery, but not a discovery of the current claim. For example, the famous example of Priestley famously found the dephlogisticated air, as he called it, and I think I pretend that this is a discovery of some previously unknown early agent, which are known properties, but this was not the discovery of oxygen. That's totally, so we should not take this way as we interpreted today what he found there. One clear conclusion is that we should not collapse separate innovative steps into one large invention or one large discovery. Examining the actual techniques of invention and their contemporary understanding, the historian can show that the invention was conceived as such at the time. This is highly important since, as Schaffer showed, discoveries have been made up retrospectively in a few famous cases. This, I add, is also the case with inventions. I mean that there are often, perhaps better to turn on the last one. I mean that in many cases, many times they are also for invention, or there is a reference as though they were invented before the usual one. במקום אייל, שלא יפעיל, בסדר. From this kind of concrete definition, it follows that mere ideas or general suggestion about a possible technique are far from a working device and should not be regarded as its invention. And this is what Amichai just said about the idea that we'll have a hydrogen bomb. Is not invention. Likewise, a suggestive hypothesis presented as prediction is far from a strong claim and even farther from a discovery. General ideas are much easier to produce than empirically based rigorous theories. Empirical evidence for their existence and actual techniques. We should not confuse the temptation to find that the statement agrees with later developments, which is easier, the more general the first claim is. So we should not confuse this kind of temptation of finding some agreements with the claim that the later discovery or technique had already existed somehow in the earlier statement, which is a classical projection bias. Indeed, an examination of a large predecessor shows large gaps between them and the later inventions. This should serve as an antidote against the fixation with the first two suggested, which is a common fallacy in various kinds of popular histories, and sadly also in some more professional histories. How much time do I have?
10 minutes.
Okay, so I'll take you 5 more. So I'll give the second, one more example is that I would like to say that the discovery of the retardation of the Earth's daily rotation and its fluctuations is a case that demonstrates the problematics in retrospective attribution of a discovery, and also of what we can take as a prediction, and the long process often required to establish a discovery. So this is from a different project of mine, not of a multiple, but I think it's very connected to our talk, to our subject today. So early conjectures about that the Earth retards were based on general notion that friction should cause slowing down of the Earth. This could be at best regarded as a successful guesses. I claim this because they lack knowledge. There was no knowledge in the prediction about the order of magnitude of the effect. That is, if it is close to the observable effect that we could view. So if we talk about changes of seconds per century, millisecond per century, microsecond per century, minutes per century, there was no way to do that, and then there was no way to do whether it's connected to the phenomenon, because if it's microseconds, there is nothing, because we cannot detect it, and there are so many other things in the world that interact and interfere. Moreover, they ignored possible other effects that might have compensated or been the genuine cause of the effect had the effect existed. The other connected hypothesis is that of terrestrial fluctuations. They were first conjectured to explain one phenomenon, residuals, or what is called deviations in the motion of the moon. But this one phenomenon might have other causes. Without observing the effect in other cases, the hypothesis was very far from a discovery. At the beginning, they said that you cannot see it in other planets because you don't have information exact enough. So then it is a possible hypothesis, but that's an hypothesis. The early claim that the effect of the fluctuations were observed in other phenomena were based, however, on problematic and even later seen as mistaken inference and data. So, were there a discovery? But so we have the argument but when the argument for a claim is invalid, I would say that it should not be regarded as a genuine discovery, even in the case that later it was found correct, because of course logically it's very clear that later it would have found also incorrect. There was no basis for that from the first inference. Early valid claims for evidence to the fluctuations were based on small set of phenomena and also included some mistakes. Were they the discovery? Or is it better in such cases to look at the establishment of the claim about nature rather than at the discovery? So we have a longer process. This was a process that required the accumulation of analysis and data by quite a few astronomers and exchange among them. No person should be regarded as the discoverer, as there was no one point of discovery. Similar, here also we have some, in this case, I think it is useful to examine the community's reception and judgment to at least put when it was established, if not discovered. And this is, I think, somewhat connected to Guy's talk, whether the community is important and when. I would say that also that a similar phenomenon is presented by what I call cumulative inventions, where you cannot say when the invention started, but you can say that there is something, some kind of a long continuum. The process of realization of the Earth's speculations also suggests the difficulties in turning observations into evidence due to the complicated analysis of the raw data, the effect of the instrument, and the need to compare measurements to extend theory. This, we saw earlier, was also the case with CMB. Thus, rarely they are simple observations that one can interpret as evidence for a new effect. Often, discovery is turning of observations into an effect. Thank you.